welcome to today's webinar. Our presenters today are Mark Porter and Kevin Jernigan. Mark is the General Manager of RDS, and Kevin is a Senior Product Manager in the Amazon RDS team. Today with us, we also have Kamal Patel, Grant McAllister, and David Wien. They will serve as our webinar moderators and will be engaging with you and answering questions throughout the presentation. Mark, Kevin, welcome. The floor is now yours.
Hey, everybody.
Yeah, thanks, Ryan. This is Kevin Jernigan. As Ryan said, I'm the Senior Product Manager for Amazon Aurora with Postgres compatibility. And I'm happy to welcome Mark Porter, who is the General Manager for both Amazon Aurora Postgres and Amazon RDS for Postgres. And so Mark's going to start us off on today's webinar, and we'll trade back and forth as we go through today's slides. So take it away, Mark.
Hey, everybody. Thanks for joining. Today, one of the things we want to accomplish is to give you guys the gift of information. Thank you all for joining. And part of giving you the gift of information is having you ask lots of questions, which is why we've staffed this with moderators. So please ask any and all questions, and we'll try to get to every single one for you. So let's go over what we're going to chat about today. We're going to chat about why we built Amazon Aurora. We're going to go through some fast facts. We're going to talk about the durability and availability and performance. We're going to go a little bit deeper into a new feature, which we announced at reInvent, and then we're going to go through the feature roadmap. And at the end of this, we're going to give you information on signing up for the preview if you haven't already, and we're going to take questions. So the first question which a lot of people ask us is, why did we build Amazon Aurora? And I think it's really important because it's not just another relational database or another instantiation of an open source database on AWS. It's a fundamental game changer. And we're actually proud of that game changer, but at the same time, we'll be vocally self-critical and say that while we've been developing this product for 5 years, we continue to find new ways that the cloud native nature of Amazon Aurora can benefit our users. So a good place to start is to look at traditional relational databases like Oracle, Postgres, MySQL, SQL Server. They have this monolithic stack. In this monolithic stack, nothing scales independently. You have to scale up all the machines together. You have to scale up all your storage. And nothing fails independently either. In fact, we often refer to this as the lowest performance denominator, or LPD, and lowest availability denominator, or LAD. In fact, one of the reasons the NoSQL movement has been so successful is that people needed to scale their databases. So the funny thing about NoSQL, though, is that no one ever said they didn't want transactions. They just wanted massive scalability. So let's look back over the last 20 to 30 years of what people did to scale their databases. Well, the first thing they did is they tried sharding. In a sense, this scales, but you lose the ability to join your data sets, and your application becomes far more complex. Sharding is still in use today, largely in the MySQL world, but about the only good thing you can say about sharding is that it's not one of the other two complicated solutions on this slide. Second, people tried to couple at the SQL layer, and this was instantiated with two-phase commit. While this was arguably simpler from an application design, the performance was abysmal, and in fact, two-phase commit is not a common design pattern for any major database applications today. Finally, people decided to throw an intense amount of science at the problem, and this is where they did shared disk, coupling buffer caches together and storage together at the same time. For example, this is the architecture of Oracle RAC. While people worked on this technology and loved the challenge of it, arguably no one has gotten it right yet. For example, most mission-critical RAC clusters are complex to use, incredibly expensive, and no offense to great DBAs, which I've been one, and a lot of people on this call have been one, but they have a bunch of highly paid DBAs dancing around them, reconfiguring all the time. So in summary, none of these architectures have worked to provide simple, inexpensive scaling because they all continue to have the weakness of too much interlayer coupling. So what if you were reimagining the database today? Well, you'd break apart the stack because you'd have the ability to be flexible at any layer of the stack, and you'd have it scale out at the layers you needed. You'd have those layers be self-healing, and you'd have them leverage distributed services. So That's a lot of what we did. You'd move the logging and storage layer into a multi-tenant, scale-out, database-optimized storage service. You'd integrate that storage service and the database with other services like EC2, VPC, DynamoDB, Amazon Route 53. And you'd make both the database service and the storage service managed services. And so that's a lot of what we did in Amazon Aurora. And in fact, this project goes all the way back to 2012. So in 2014, we launched Amazon Aurora with MySQL compatibility. And one of the stories I like to tell is that when we launched in 2014, I had 16 customer meetings over the next 2 days. And in 14 of them, people said, well, when are you going to add Postgres compatibility? It wasn't that they didn't like MySQL compatibility, they just wanted Postgres too. So we just announced Postgres compatibility, and now you can choose to get all the benefits of that decoupled storage system at the same time as using either Postgres or MySQL applications. So now what we're going to do is, for those of you who might not be familiar with Postgres, we want to go through and acquaint you with why Postgres is an awesome system and some of the things which made us very excited to add it to the Amazon Aurora family. So Kevin, take it away.
Great, thanks, Mark. Yeah, and it is interesting to dive into some of the details of why Postgres has been in such high demand from our customers. And so some of the things our customers tell us are that they like about Postgres include these. It's an open source project that started more than 20 years ago as a follow-on to the Ingress database system, for those of you who remember Ingress back in the day. And Postgres itself has, that open source project has a really active and vibrant community that continues to innovate, continues to add new features and capabilities. And this is partially due to the type of open source license used by the Postgres project, which pretty much allows anyone to modify the source code as needed. In addition, Postgres is not owned or controlled by a single company. It is owned by a nonprofit foundation, which helps address customer concerns about vendor lock-in. From the perspective of functionality, Postgres offers good performance out of the box. And with transactional semantics similar to those of Oracle and SQL Server. In addition, Postgres is object-oriented, it's ANSI SQL 2008 compatible, which makes it easy for customers to migrate applications to Postgres from other relational databases. And Postgres also has very strong support for geospatial capabilities with the PostGIS extension, and supports stored procedures in many languages, including PL/PG-SQL, which is very similar to Oracle's PL/SQL. And so what do we mean when we say we've made Amazon Aurora compatible with Postgres? Well, we started with the Postgres 9.6 code, which is the current production version of Postgres available from the community. And we've integrated Amazon Aurora's cloud-optimized storage into the lower layers of that code. Now, Amazon Aurora maintains 6 copies of every write across 3 availability zones for high durability. It supports up to 15 read replicas with very low replica lag. It provides failover times of 30 seconds or less, and we're currently seeing performance greater than or equal to 2 times that of standard Postgres on standard benchmarks. Amazon Aurora Storage, of course, also includes cloud-native security and encryption. It's integrated with AWS Key Management Service and AWS Identity and Access Management. We've also integrated it into Amazon RDS, of course, making it easy to provision and manage. And customers can use AWS Database Migration Service and Schema Conversion Tool to migrate data into Aurora with Postgres compatibility, and also to migrate data out if needed. It's important to keep in mind that we're running Postgres code. We're not emulating or simulating Postgres functionality with a compatibility layer. We're running the core Postgres code. And the Postgres compatible edition of Amazon Aurora is a native Postgres implementation. And we plan to maintain compatibility with Postgres for the foreseeable future. Now I'm going to hand it back to Mark. He's going to dive deeper into the durability and availability that Amazon Aurora with Postgres compatibility provides.
Thanks, Kevin. So one of the things I think I want to emphasize here today is that Kevin and I have been in the database industry, and so is Grant and a couple other people on the moderator panel, our entire careers. And in fact, people often say that my career is an exercise in worshiping the ACID transaction. And one of the most exciting things about Aurora is that by decoupling, as I'm going to describe here in a minute, we actually take over many of the durability and availability concerns that DBAs and administrators spend a large percentage of their time doing. So as you listen to my next slides, think about not only the cool technology, which we're really excited about and think is pretty awesome, but at the same time, think about what this allows you not to spend your time doing so that you can spend your time doing other things. So the first thing we did is we took that storage, and on this slide you'll see the primary database node in availability zone 1, and then you'll see read replicas in availability zones 2 and 3, and we took the storage away. But the key thing to walk away with here is this is not just putting the disks in other storage areas. This is actually making a storage system which is transaction aware. And it has its own copies, so it takes care of itself. It has its own monitoring service that repairs it when it's needed, and it's spread across an entire AWS region so that your application servers can fundamentally live anywhere. And so when you look upon how the storage engine works, and it's the same storage engine fundamentally between Amazon Aurora with MySQL compatibility and Amazon Aurora with Postgres compatibility, it actually writes every single write 6 times. Now, that's a lot of writes, there's no doubt about it. However, the interesting thing about Amazon Aurora is it's only writing what you in Oracle land would refer to as redo records or log records, which means that the data actually ends up being a lot less data. I'll get that into a little bit more detail later. The other thing to realize is that data is continually backed up to S3. There's no backup windows. The concept doesn't even exist for Amazon Aurora. There's no performance impact during backup. The system has a separate monitoring and management layer that you'll never see as a customer. We ran it internally. To you, the databases just keep running along with the storage underneath them. Aurora also has a quorum algorithm for writes. As soon as 4 of the 6 writes are durable, the system can return a committed transaction. What this means is that lagging disks or nodes can just be ridden through by the system with little or no impact on performance. And as administrators, the system actually will notice those lagging disks or nodes and go fix it long before they ever impact database performance. Not only that, nodes can join and leave the system as they're upgraded or repaired, and there's absolutely no performance or availability impact. And in fact, as a customer, you don't even know this is happening. So the other advantage here is that Amazon Aurora grows automatically up to 64 terabytes, which is a real win for many systems, and it's really easy for you to manage as opposed to either managing 64 terabytes in EC2 on-premise or even in RDS, which only goes up to 6 terabytes right now. So there's a lot of things that can fail. The little x there on the left side is a segment has failed, which means a disk has failed. The second X on the left side, the medium side, is that an entire node can fail. And the third is that an entire availability zone doesn't fail. We've never had an AZ fail at Amazon, but it could have some network impairment getting to it from the other nodes. And Amazon Aurora will ride through all of these things with no impact on database availability. And as I've described, we use 4 out of 6 write quorum. We also use 3 out of 6 read quorum, which means even if 3 of your 6 copies go away, the system will continue serving reads. Not only that, the system repairs itself. These sideways arrows you see between the storage nodes actually are the nodes chatting with each other, and if one of them has gone offline or needs to be repaired or missed a write, they'll actually chat with each other to repair it using the network bandwidth between those nodes and the CPU on those nodes, not the CPU or network bandwidth of your main node. Amazon Aurora, we're going to step up from the storage layer and we're going to talk about the database layer. Just like the storage layer, there's a separate monitoring and repair system. One that you won't really see as a customer as it does most of its work. At any time, Amazon Aurora provides one primary writable database node and up to 15 read-only replicas. These nodes are monitored and replaced as needed. Not only that, the system detects failing database processes, not just nodes, and recycles them as needed. And then because of the optimizations we've made, these read replicas typically lag the master by less than 10 milliseconds. Notice that I said milliseconds, not seconds. For those of you who are familiar with Postgres, Postgres typically on large systems runs between 100 and 120 millisecond lag time. MySQL runs in the multiple seconds of lag time. And so I'm going to reinforce milliseconds. And what this has done is this has allowed customers to start moving loads to read replicas which they never thought of moving. As a database administrator, you want to have your backups running all the time. You want to have the ability to restore. Amazon Aurora does this in the background all the time. It continually writes snapshots of each 10 gig segment to S3. And in the event of restoring to a new volume, instead of the backup being single-threaded through your database node, a problem that we always have on a traditional architecture, the literally hundreds of storage nodes in a storage cluster can all access Amazon S3 in parallel and apply the logs simultaneously and the segments, giving the absolute fastest possible restore time. One subtlety, for those of you familiar with relational databases, is instant crash recovery. A traditional database has to replay logs since the last checkpoint. Those checkpoints are typically 5 minutes, and this recovery can either be single-threaded or multi-threaded, but it takes a long time and it's all single-threaded through the head node. Because Amazon Aurora is actually playing log records out to the storage system, there is actually no recovery. You just tell the storage system, I would like to have you be concurrent, and you give it, the database gives it a system commit number or logical sequence number, and it's just there. You'll see later in the presentation a little bit about that performance benefit. Not only that, Amazon Aurora makes predictable failover. We all understand that in large systems things do fail, either because of software errors or hardware errors. And switches fail, CPUs fail, power supplies stop working. So there's no option to be clever and restart the database. The database node just isn't there anymore. So when the node fails, you actually have to promote another database node to be the master. And in Amazon RDS for Postgres, we do this pretty well, detecting the failure in 15 to 20 seconds. We then do DNS propagation and recovery in parallel, and we get the node available to the world again in about 60 seconds for most of our recoveries. In Aurora, recovery almost never takes longer than the DNS propagation, shortening failover time significantly. In addition, if you've written an application that uses our cluster-aware drivers, the ones that don't depend on DNS propagation, you can be up and running even before the DNS change is completed. Combining these features means that most failovers occur in 30 seconds or less. So, for your reference, this slide took much longer to go through than 99% of Amazon Aurora failovers. So now we're going to go through some of the performance that we've gotten, and Kevin's going to go through some slides showing different dimensions of performance.
All right, thanks, Mark. I'm excited to dive in on some of these recent benchmark results. From the beginning, performance has been one of the major goals for this project. It has been to deliver better performance for demanding workloads from customers. And so as part of our performance effort, we run standard benchmarks to compare with standard Postgres. And so before we get into all the fancy graphs, I just want to give you a little setup here. All the tests were done with the database engine running on an M4.16x large, with the clients running on a C4.8x large, and the client and database nodes were in the same availability zone. For the Postgres tests, we used version 9.6.1, and we used 3 provisioned IOPS volumes of 3,000 gig each for a total of 45,000 IOPS. We created an ext4 file system striped across a logical volume on top of that storage, and we also enabled full page writes, checksums, and wall compression. This combination gives the best performance for Postgres while also most directly comparing with the durability and availability built into Amazon Aurora storage. So let's first look at some pgbench results. pgbench is the standard benchmark that's part of the Postgres distribution, and it has several built-in modes. One of those modes is TPCB-like, in which pgbench runs transactions that are very similar to the standard TPCB transaction. So we ran PGBench in TPCB-like mode while increasing the number of client connections from 256 up to 1,536. And we used a 30 gig scale 2000 size database, and we ran each test for 60 minutes. Now, as you can see in the graph, Postgres reaches a peak of just under 18,000 transactions per second at 512 connections, whereas Amazon Aurora continues to scale up as more connections are added, reaching a peak of just over 38,000 transactions per second at 1,024 connections. So the peak-to-peak comparison shows Amazon Aurora delivers more than 2x the throughput on Postgres, and the direct comparison of Amazon Aurora's peak with the corresponding Postgres result with 1,024 connections shows a ratio of greater than 2.5 times. So in this next test, we use Sysbench, a benchmark utility often used to compare different database engines. And we ran the Sysbench write-only benchmark, again while increasing the number of client connections with a 30 gig database. Now, Postgres scales up until reaching more than 47,000 writes per second at 1,024 connections, then the throughput drops as more connections are added. Aurora scales up to more than 92,000 writes per second at 1,536 connections, about 2 times more throughput when comparing peak to peak. Compared directly with the Postgres throughput at 1,536 connections, the ratio is, again, more than 2.5x. Another metric we like to track closely in our benchmarking is writes per second with Sysbench. So in this screenshot, you can see the results of a Sysbench run with an average of more than 120,000 writes per second. You'll also notice that the reads were 0. This was truly a write-only configuration of Sysbench. Now let's take a look at data load performance. With the PGBench benchmark, you of course have to first load the database. So we compare the time it takes to load, vacuum, and build indexes for a scale 10,000 or 150 gigabyte PGBench database. Now, as you can see, Amazon Aurora can finish that PGBench initialization phase about 3 times faster than Postgres. Now, most of the performance difference in load times is due to the database-specific storage optimizations that are one of the keys to Amazon Aurora storage, and Mark will dive deeper into those optimizations in just a few minutes. And now, a couple other interesting graphs here. It's important to measure throughput, but it's also important to measure response time at scale. And so we looked at Sysbench response times with 1,024 concurrent connections. And on the graph, you can see very different behavior for Aurora as compared with Postgres. The response times for Aurora are much steadier with much less volatility, much less variation. And more precisely, based on measuring standard deviations of these data sets, Amazon Aurora is more than 10 times more consistent than Postgres. And the average response time is also about 2.9x lower. So Aurora delivers much faster response times with much less variability. Now you might wonder what's going on with those Postgres results, and what you see is the impact of database checkpoints, which Postgres does to ensure that dirty pages in memory are periodically written to storage to ensure recovery time from a crash isn't extended too long. And this is a typical thing that most database systems have to do. They have to periodically checkpoint. And during a checkpoint, that means Postgres will do a lot of writes, which will slow down user transactions, and hence you see this variability in the Postgres response times. Now, let's go back to PGBench to look at some consistent performance based upon throughput. In this graph, higher is better, as we're showing the throughput while running PGBench in TPCB-like mode. We ran each database at the optimal number of clients to deliver max throughput for that database and plotted the variability in throughput over time. As you can see, again, Amazon Aurora is much more consistent and delivers significantly higher throughput. Based on standard deviation, Aurora is about 3 times more consistent than Postgres. So let's look at how Amazon Aurora performs at large scales. And you can see that as we increase the database size from 10 gig to 100 gig with Sysbench in the write-only configuration, the Aurora performance, the Aurora throughput, doesn't drop off as much as Postgres does. Now, we of course would like to see it not drop off at all, but you can see it maintains better throughput even on larger scale databases than Postgres. Now, another interesting thing to think about, and this goes back to the checkpoint discussion a few slides ago, is recovery time, especially recovery time when you're running a heavily loaded system and you have a node crash or a database crash. And so you can see we did different configurations of Postgres to configure the frequency of checkpoints, to change the frequency of checkpoints. Because, of course, if you make the interval between checkpoints longer, then that variability you saw in response time and throughput will be lessened, with the penalty that recovery time will be longer on a crash. And so that's what you see in those three blue bar examples with different size checkpoints for Postgres. And you can see the bigger the checkpoint interval, the longer the recovery time, up to 102 seconds for the biggest checkpoint configuration. Well, with Amazon Aurora, we don't really need to do checkpoints at all. And so regardless of the throughput or the load on the database, the recovery time is very, very short. So, it didn't matter what checkpoint configuration it was because it's not really a need to do checkpoints. The recovery time is 1.2 seconds in all cases. And so in this scenario, we're delivering about 85 times faster recovery times. So this slide summarizes what we just covered in the last performance slide. We showed results from both PGBench and SysBench, demonstrating throughput 2x to 3x that of Postgres. We've also showed data loading 3 times faster. We showed response times to be more than 2 times faster, and both response times and throughput to be much more consistent. We showed throughput at larger scale databases to be 3 times faster, and we showed recovery speed to be much, much faster due to the innovations in the underlying Aurora storage. So the performance results are impressive that we just reviewed. I briefly touched on how we're achieving those numbers, but I'm going to hand it back off to Mark now so he can dive deeper into more details on how we deliver these results.
Thanks, Kevin. So as I listened to Kevin talk today, I was thinking to myself, if I was one of you guys on the call, what would I be thinking? And one of the things I'd be thinking is, I want to run my database. I want to have it be available all the time. And so we've been working on that. I want to have it be durable so I never lose my data and I don't have to manage that and worry about it. And I want to be performant. And those are, the 3 main things. And when we talk about all these benchmarks, I want to be sure you don't walk away thinking that we're just indexed on benchmarks. As we've been bringing people into the preview, we are taking people's real-world loads on board, and we're actually starting to, profile those as well. So if you guys join the preview and you bring your real-world testing of your application on board, we'd love that. So don't think we're just focused on benchmarks, but they are a way for us to communicate a consistent set of numbers with people in the community. So now I'm going to talk a little bit about how Amazon Aurora achieves performance, and this will give you a hint of where we're going to be going over the coming years as we continue to enhance performance, both for benchmarks and for real-world applications. So the key tenets of performance are that the best way to have higher performance is to do less work, do fewer IOs, do smaller IOs, minimize network packets. And in particular, unless you're going to go to a multi-writer scenario like Oracle RAC, which, as I said earlier, we think is a bad idea right now, you need to offload the database engine so it can do more. Not only that, you want to reduce the latency path, you want to use lock-free data structures wherever possible, and you want to batch stuff together. So how, for example, does IO traffic in Amazon RDS work? Well, Amazon RDS has a primary database node, a standby database node, and it will write to 4 copies of the data are stored across 2 availability zones. This works great and helps us run the largest fleet of Postgres databases in the world with very high availability and durability. However, because this uses the monolithic traditional database stack, even on the AWS cloud, you can only take it so far. In particular, note that steps 1, 3, and 5 are sequential and synchronous, and this amplifies both latency, which most mission-critical apps can live with, but it also amplifies jitter. And one of the things you saw on Kevin's performance slide is that jitter is very minimized on Amazon Aurora. How does it work in Aurora? Well, the first thing we do is we do things differently. We're using the 4 out of 6 quorum. We reduce I/O and network jitter. We sort writes into buckets per storage node, so we get more efficiency out of the network. And because the storage system is transaction aware, it doesn't acknowledge writes coming back. It acknowledges groups of transactions. Note the difference there, groups of actual transactions. This minimizes a lot of the chatter between the storage nodes and the head nodes. So while we do more than 6 times the number of logical writes than a normal monolithic database, in our measurements between packing commits together and only writing log records, it actually ends up that we're doing about 9x less network traffic. So down there in the magic are these storage nodes we've been talking about. So this slide dives into a little bit about what's going on in those storage nodes. Those batches of log records have to go somewhere. So let's dive into the architecture of the node. If you take away only one thing from this slide, it would be that only operations 1 and 2, receiving the batch of log records and persisting it in log form to a local SSD and acknowledging it back, block database operations. The rest of the system is completely asynchronous to the database. These operations include gossiping with other storage nodes, coalescing log records into data blocks, backup and doing garbage collection, and even background verification checks on the storage all the time. Amazon Aurora also supports read replicas, and let's quickly touch on how it works. In Postgres, the redo wall is shipped from the master to the replica, written to disk, and then applied in a single-threaded process. When the replica applies the redo, it reads in the block, if not already in memory, and then those change blocks need to be written to the replica data block volume. It's an awful lot of I/O being done on a replica. On Aurora, the changes are shipped to the replica and applied to the cache pages and don't need to be written out. Currently, Aurora will read pages from storage to apply redo if not cached. Since there are no writes being done on the replica, it means there are more resources available to support read queries, which means that your replicas can actually do more work for you. One of the biggest problems with traditional databases is that when the database process itself dies, the buffer cache, which in modern databases can be gigabytes, dies with it. This means that when the database restarts, it's a very, very cold start, is what we say in the database world, and application performance can be affected for many minutes. For example, if you have a 200 gig database cache, even if you refill blocks at 1 gig per second, it's over 3 minutes before the application's running at full speed again. So this is a lot trickier than it looks. What we did is we actually keep the database cache around between restarts. When the database process comes back up, there are many data structures in shared memory which might have actually been in the process of modification when the database process crashed. A very quick verification process is started to verify those in-memory data structures. In particular, the very small percentage of the buffers in the cache which were modified for uncommitted transactions are discarded. No committed transactions are lost in any part of Amazon Aurora or in this. And what this means is that not only is the database back up and running, but your applications are back up and running. So this is really important to actually having your website start serving all of its transactions again once the database crashes. So now what we're going to do is we're going to talk about something where we wanted users to be able to see much better performance information. So Kevin, I'm handing it over to you.
Great, thanks. So having a high-performance system is great, but sometimes things don't go as planned. Even in a managed database system like RDS, and Aurora is part of RDS, you need to understand what's going on. So earlier this year, we released enhanced OS monitoring for Amazon RDS, allowing you to see 57 per second statistics on your database instance, things like what you'd get with VMstat or IOstat or TOP, etc. And that's great, and customers have told us how much it's helped them. However, we wanted to deliver more. And I bet you think you want to be able to look inside your database, not just inside your operating system. And we thought so too. So we're announcing Performance Insights, which is a new feature that will roll out first in the Postgres edition of Amazon Aurora, and then will make its way into all 7 RDS managed databases. And now, as I mentioned, over the past year, we began improving visibility into RDS with enhanced monitoring, which provides detailed metrics from the underlying operating system. Gives you the kind of data you would get from VMstat and IOstat. It also includes process and thread listing, which provides a view similar to the Linux top command, which lets you see which database processes are consuming the most CPU and the most memory. Performance Insights is the next step, and it goes beyond OS metrics to dive deep into the database engine itself. It's a new feature of RDS, which provides an intuitive way to tune database workloads even if you aren't a database tuning expert. We've heard from our customers that while they love how RDS manages many of the rote tasks of database management, they'd really like one more of those tasks simplified and managed, and that is database tuning. And we understood from the start that many of those using our services may not be expert DBAs or database tuning experts. So we decided to try to design an approach that would make tuning intuitive with a simple dashboard view that would naturally expose performance problems and let you drill down from there. And so RDS is all about managed databases. Customers want their performance managed as well. And they really, in addition to being able to do this without a lot of deep expertise, they also want a single pane of glass where they can see all of their performance metrics together. And so at this top level view, you can see a few details here. Performance Insights will give you both API access to the time series of sample data and also, of course, visualization of this data. And this visualization will allow you to easily see how your database time has been consumed over the recent past. And you can see in this example, you can see database load broken down by different types of activities within the database and a visually proportional representation of how those different times were consumed. And so how does Performance Insights actually help you find the root cause of problems? Well, as you'd expect, we show you the database engine metrics that you're accustomed to getting from your own scripts and from third-party database tuning tools. And you can select which metrics out of hundreds you want to have displayed in this top graph. But we're also innovating beyond that, to provide guided discovery of performance problems underneath. And Performance Insights centers around a core metric called database load. It's a metric that makes performance bottlenecks stand out and helps guide users to the root of problems. And so database load is front and center in Performance Insights. And you can see how graphing this metric tells you how saturated the database is and also tells you what's responsible for the workload. In this screenshot, for example, we can see that we're looking at a database that is heavily loaded compared to the number of vCPUs. Now the console UI has the ability to zoom in to the 5-minute level or out to a variety of levels up to 35 days. By default, we see database load is broken down by wait event, which tells you the type of activity that is consuming the load, but you can also choose to break down the load by any of these dimensions. Below the database load chart, we see a list of the top SQL. This is also ordered by database load. And from this list, you can see which SQL is most responsible for load in the database and the type of activity that is causing each of those to consume load. And you can see some of these are very CPU dominant. And so it's hard to miss that. When using weights as our dimension, there's a large chunk of unknown. This is because the Postgres compatible kernel is not yet 100% instrumented with wait events. And as instrumentation is added to the system, the amount of unknown wait time will eventually disappear. You also might have noticed that some of the SQL statements have question marks instead of real values in certain places. This is because we're normalizing large numbers of very similar SQLs that differ only by the values in the where clause, into buckets that we call digests, so that we can characterize them here as a single logical SQL. That way we show you the real impact of the SQL in total. If you want to know what the SQLs comprising that digest look like, you can drill down into the details within this user interface. And so once you've selected one digest, you can also see that the load graph will highlight the component of the workload that SQL is responsible for. Performance Insights has a bunch of other great features such as lock detection. It'll show you execution plans and of course API access to all the data. It's included with RDS at no additional charge and includes 35 days of performance data retention. Now we're making it available initially with the Postgres compatible edition of Aurora, but you can expect it to cover the remaining RDS engines over the course of 2017. So if you're in the preview for the Postgres compatible edition of Aurora, make sure to ask your TAM or AWS representative to request to also be whitelisted for the preview of Performance Insights. Now I'm going to review our roadmap for Amazon Aurora with Postgres compatibility, so you get a little more detail on what we plan to include when we go GA. And as you can see, we plan to launch with a whole bunch of features. I'm not going to read through all the features on this slide, but I do want to highlight a few. We've already reviewed the performance benefits in detail, so I won't cover that. But in the area of operability and compatibility, we plan to support all Postgres 9.6.1 features, all RDS for Postgres extensions, and inbound migrations using both Snapshot Import and AWS Database Migration Service. For high availability, we will support instant crash recovery. Remember the difference in recovery time as compared with standard Postgres, and up to 15 read replicas, which will allow customers to scale out read performance and read workloads. And of course, we're building in security from the ground up with support for encryption at rest, encryption in transit, VPC, and row-level security, just to name a few things. And all of these features are planned for the initial release. And this slide tries to show how the Postgres compatible edition is part of the Amazon Aurora database family. And you know, at Amazon, we always start with security, and that's why it's at the top of this slide. I already mentioned the integration that we're implementing with both KMS and IAM, and of course encryption at rest and in transit. As we go around this circle and look at high performance and scale, we've shown you the performance graphs in terms of just the throughput and response time, but also should point out again that Amazon Aurora dynamically and automatically will scale your database up to 64 terabytes. So that's a much higher limit than the current possibilities with RDS. Compatibility, of course, we talked about. Aurora has a MySQL compatible edition and now the Postgres compatible edition. The convenience of RDS and DMS makes it easy to both manage your databases inside of RDS with Aurora and with DMS to move data in and out of Aurora as you need to. In availability, we of course have read replicas, which lets you scale out to up to 15 of them, and all the built-in capabilities of the underlying Aurora storage, including automatic failover. And as I think we pointed out, our goal is a failover to make failover happen very quickly, ideally to a warm cache, so that your performance is high from the time you connect to the new primary after a failover. And finally, durability, the underlying capabilities of Amazon Aurora with 6 copies across 3 AZs, plus continuous backups to S3 and other features, gives very high durability for the data stored in an Amazon Aurora database. So we're going to go through some of the questions in the Q&A now, but a few things on timeline first. As we mentioned along the way, we are currently in preview mode. We're taking signups for the preview now. You can actually sign up by clicking on the link you see on this slide. And we are adding more customers as we continue to grow the capacity of the system itself and move towards GA. We do plan to release this service in general availability in 2017, sometime later this year. And love to have more people in the preview, of course. There's also FAQs available at the link you see below. And of course, you can reach both Mark and I by email at the email addresses you see on the slide. So I'm going to leave this slide up while we take a look at some of the